All right, so we're going to go over some enrichment problems using calculations that we learned for weak acids and bases. All right, so in this first problem, we've got chloroacetic acid, and we know it's Ka, and we want to know these three things. So we first need to write our dissociation equation. So ClCH2CO2H, AQ plus water is in equilibrium with H3O plus and chloroacetate. Oops, CO2 minus. And we know the Ka value. We want to know pH. So we first need to make our ice table, right? And we know the concentration is 0.1 molar. And this is who cares, and this is 0. And this is going to go up by x. And so this is going to go down by x. We're going to make the 1.15, 0.10. We're going to make the 5% approximation because Ka is so small, right? So we would say to ourselves, okay, Ka is equal to H3O plus times chloroacetate forgot my charge for chloroacetic acid. And then we just plug in all our values. So 1.35 times 10 to the negative third is equal to, excuse me, x squared over 0.10. So I got x equals, what did I get? 0.0116. Did you? Do we agree? Now we're going to plug that back in as x. And then how would I get the pH? The pH would just be the negative log of H3O plus, right? So that's negative log of 0.0116. And let's see, we have two sig figs here, so we're going to have two decimal places in our pH. So I got 1.93. Do we agree? All right, for the percent dissociation, that would be my H3O plus at equilibrium over the acid concentration that I began with. So that would be 0.0116 divided by 0.1 times 100. So I got 11.6%. Did you? 11.6%. Percent dissociation would be the amount we get at equilibrium divided by the amount we began with times 100. Do we agree? And then for pKa, that's just negative log of the Ka, which is right here. So we just dump that value in. So I got, now that's got 3 sig figs, so I'll need 3 decimal places. 2.870. Do we agree on these values? Any questions on number 1? We good on number 1? All right, let's look at number 2. Let me give myself a little bit more room to write this time. And make that a little bit bigger. There we go. Okay. I'm studying this acid, and I determined the pH of this particular molarity to be 3.77. I wanted the Ka and the percent dissociation. So the first thing I have to do for any of these acid calculations is write our dissociation. So HC3H5O2 plus H2O is in equilibrium with H3O plus C3H5O2 minus. Okay, now if I were to make an ice table for this, right, ICE, this is a 1 times 10 to the negative 2 molar solution, right, so that's 0.01, who cares, 0, 0, plus X, this is going to be minus X, 0.01 minus X. We don't make the 5% approximation here, right? We do not. No 5%. Because X is known accurately. Right? And how do I get X? Well, the problem tells me the pH, right? If pH is 3.77, then H3O plus, which is the value of X, would be 10 to the negative pH. So that's 10 to the negative 3.77. So I got 1.698 times 10 to the negative fourth. Right? Do we agree on that value for X? Again, we're going to plug in. Now, when I subtract that within sig figs, this is not going to change anything. Right? So that still ends up being 0.01. Because 0.01 minus times 10 to the negative fourth isn't going to make a difference. So now, Ka is just H3O plus times my anion over the acid. So plugging all my values in, that will be 1.698 times 10 to the negative fourth, and I'm just squaring that, right, because these two values are the same, divided by 0.01. And let's see, I got 2.88 times 10 to the negative 6. That's a reasonable Ka, right? This is a weak acid. And then how would I get percent dissociation? The same way I did in the previous problem, right? This is just going to be H3O plus over my initial concentration times 100. So that would be 1.698 times 10 to the negative fourth divided by 0.01 times 100. So I got 1.7. How many sig figs am I keeping here? 2. Yeah, 1.70%. Oh wait, 2 sig figs. Well, no, I'd have 3 sig figs. 3 and 3. Didn't take the log, so I'm just using regular sig fig rules. All right. So, any questions on number 2? Feeling good on 2? Let's do number 3. Give myself a little more room here. All right, so we have an unknown weak acid. We're just going to call it HX. We still need to write a dissociation equation for it. Okay, and we have a 0.150 molar. And this is going to go up by x. This is going to go up by x. This is going to go down by x. And this will be 0.150 minus x. And we're told that it's 3% dissociated. All right, so percent dissociation is H3O plus over HX initial times 100, right? So if this is 3%, 3% as a decimal would be 1, 2, right? 0.03. Got to carry that sig fig with me though. So if I plug this in right here, 0.030, and I know the initial concentration, that's right here, I can solve for x, right? X will be H3O plus. When I multiply those two together, I got 0.0045, which I can now plug in. So when I plug that into my ICE table, I get 0.1455, and then obviously that value just is in there directly. So now I can do all my calculations. So my Ka would be H3O plus times X minus over HX. So that would be 0.0045 squared. Since those two are the same. Divided by my HX value, 0.1455. So I got 1.39 times 10 to the negative fourth, which is reasonable for a weak acid, right? pH would just be negative log of H3O plus. So negative log of 0.0045. All right, I got, let's see, we've got, how many sig figs are we dealing with here? 2. So our answer would be 2.35, 2 decimal places. And then pKa, P just means negative log, right? So negative log of Ka. So that's negative log of the Ka I just got. 1.39 times 10 to the negative fourth. So that would be 3.857. We agree on these values? Yes, no? Yes? Am I going through it too quickly? No? All right. Does anyone need me to leave this for a second before I erase it? Good? All right. Let's go to number 4. Switching gears here, now we're looking at a base. Let's give myself more room to write here. So now we're dealing with a base, right? Because ammonia is base. And so our dissociation equation is going to be different, right? Because when we look at a base, we have to treat it differently. So ammonia is NH3, right? So let's see, where's a good spot? Right here. NH3 plus H2O is in equilibrium. Now this is the donor, right? So we get NH4 plus the ammonium ion and hydroxide ion, right? And I've got the Kb, and I've got the initial concentration, so I can solve these problems just like I did on my previous ones. Still got to make an ice table. The initial concentration is 0.75. Still omit water. This is still 0. This is still 0. Plus X and plus X. And Ka is significantly less than 1, so I can make the 5% approximation. Okay. So now all I'm doing is I'm going to solve for X. So Kb would be ammonium times hydroxide over ammonia. So when I plug in my Kb value, 1.8 times 10 to the negative fifth is equal to X times X is X squared over 0.75. So I got X to be 0.00367. We'll just carry out some extra decimal places. Plug back in as X. And so when you subtract this 0.00367 from 0.75, it's still going to be 0.75 because it's not going to change in terms of sig figs. So that value won't change. So now, how do I get pH? Well, I've got to do something else first before I can calculate pH. Because when I plug this in as X, if I were to take the negative log of this right now, would that be pH? No, it wouldn't, right? I've got to calculate pOH first. So the first thing I would do to solve for part A, first you need to calculate since you only know, since X is equal to OH minus, right? We don't know H3O plus concentration. We have to solve for it. So that means pOH will be negative log of 0.00367. So I got for my pOH 2.43. 2 sig figs, therefore 2 decimal places. Now I can get pH, right? pH would just be 14 minus 2.43. So that gives me 11.57. Do we see why we have to do pOH first? Right? Because we don't have H3O plus in the base. We only have hydroxide. We don't have hydronium. So we have to calculate hydroxide concentration, which gives us pOH, which we can then convert into a pH. All right, for percent dissociation, it works the same way. So that's going to be concentration of hydroxide at equilibrium over NH3 initial. So let's plugging in our value here. For X, 0.00367 divided by my initial value, 0.75 times 100, 2 sig figs. I got 0.49%. And this is a weak base. It's got a pretty small Kb, so that makes sense for that percent dissociation. And then how would I get pKb? P just means negative log, so negative log of the Kb. So I got 4.74. 2 sig figs means 2 decimal places. Any questions on number 4? Feeling good about number 4? Yes? Need me to leave it? Nope. All right. Last one then. Number 5. Again, this is a base problem. Methylamine is a base. All right, so you're doing an experiment using methylamine, and you determine the pH of a 0.5 molar solution to 12.32. I want to know Kb and percent dissociation. So, I need to write my dissociation equation. Right, this will be CH3NH2 plus water. Water's the donor, right? So that's in equilibrium with CH3NH3 plus and OH minus. All right, so we're gonna set up an ice table. This is a 0.5 molar solution. This is initially 0 and 0. This goes down by x, 0.50 minus x, plus x, x, plus x, x. Again, no 5% approximation, because we can solve for x accurately. We don't need to approximate it, especially if we're solving for a k, because if we approximate this value, then our k value is not going to be as good as it could be. So how are we going to get x? Well, the problem tells me the pH, right? So if the pH is 12.32, then how would I get POH? The POH would just be 14 minus 12.32, right? Because pH isn't going to help me here, because that's dealing with H3O+, and there's no H3O+ here to work with. But hydroxide ion is part of this ice table, and that's something that I can use beneficially, right? So 1.68 is the POH. And if you know the POH, can you get hydroxide ion? Yeah, right? So concentration of OH minus is just 10 to the negative POH. So that's 10 to the negative 1.68. So when I did the math, that comes out to be 0.0209 is what I got. Do we agree? Which I now plug in as x. So when I plug that value in as x, I get 0.4791. Worry about sig figs later. 0.0209. 0.0209. All right, so Kb, therefore, would be CH3NH3 plus times hydroxide over CH3NH2. This value and that value are the same, so 0.0209 squared over 0.4791. So I got 9.12 times 10 to the negative fourth. Let's see, how many sig figs would that be when I round it? That'd be 2. So that's just 9.1 times 10 to the negative fourth. And then for my percent dissociation, this is just going to be my hydroxide ion at equilibrium over my initial CH3NH2 times 100, right? Because this is saying of my initial 0.5 molar, only 0.0209 molar are actually dissociated. So 0.0209 over 0.50 times 100. You would expect this to be a small number, and it is 4.2%. questions on how we did this one? The only difference between doing this one and the one we did involving the Ka is obviously we had to convert POH to pH first, but then it's off to the races exactly the same. How do you guys feel on this? Any questions on these problems? All right, that's where we will stop for today.